Hi everybody, I'm here to talk about Unikraft and how to debloat the cloud with it. Unikraft is an open source project under the auspices of the Linux Foundation and the Zen project, and this is work done in conjunction with some colleagues at Lancaster University. So if you look at the private and public cloud, it's been obviously a huge success and for good cause. There's lots of good things about it, including the fact that it's easy to use so you can get going with your business right away. It provides great scalability, so as your business and demand grows, you can sort of transparently grow with it. And it provides a multitude of services. For instance, AWS claims over 200 such services. But everything's not rosy. On the downside, the images are extremely bloated, the virtual machines. They are on all or most of the time. And of course, this is bad for the environment. So what we need to do is trim that fat in two ways. One is that we need to debloat the actual virtual machines. And the other one is that we need to stop having idle VMs running on the public cloud all the time. Part of the problem is size. And if you take your actual virtual machine and you look inside, it's made of course, your application. This is the part that you actually care about. Under that, though, inside the virtual machine, there's a lot of unused software that is actually running. And that is wasted resources. And that's essentially money you're throwing in the trash can. The second part of the problem is in the time domain. When you start your virtual machine, in the beginning it's idle. Then at some point a client request comes in, so it's actually doing some useful work, it's active. After that, though, it goes idle again, and the cycle repeats. Every time it's idle, that's wasted resources. And that's, again, money in the trash. So how do we solve this? And the answer is specialization, meaning that if you know what your target application is, you can customize your entire software stack to the needs of it and achieve high efficiency that way. In the domain of virtual machines, such specialized virtual machines are called unikernels. And there's a few goals that these should accomplish. The first one is that they should be easy to build and run. This hasn't always been the case in past unikernel projects. There should be easy or almost no application porting. This has always been a bit of an Achilles heel for unikernels. And of course, they should provide great performance. So let me show you a little bit about the potential of unikernels. In terms of migrations times and start and stop times, there's been papers that have shown that these can do so in as little as a few milliseconds. They can provide very low memory footprint, so you can run actual standard applications such as nginx in a few megs of RAM or even less. And there's some papers showing that, including one of ours that last week got the best paper award at Eurosys. They all can also provide high density, so you can imagine running thousands of these on servers, and there's papers showing this as well. They can provide high performance. You can imagine things like 300,000 requests per second on an nginx web server on a single CPU. And they have nice security features because you're essentially throwing a lot of unneeded code away since you're specializing. So just to give you a bit more details about what a unikernel actually looks like, imagine you want to run just a web server, and on a general purpose OS, you're going to have third-party libraries, lots of them, even though really what you want to use is just those two colored ones I'm showing you. The web server only needs those. Under that, you're going to have operating system libraries. And again, it's the same issue. You have lots of libraries in the image, but you only need a few. Under that, you have the OS kernel. You only need some functionality for the web server, but you have lots of things in there packed in. So what you really would like to do is, by some sort of magic, get all those colored bits and put them in a custom software stack and operating system that only has the bits that the web server needs. And that's what a unikernel actually is. The problem is that transformation has required in the past lots of development time because you had to handcraft each unikernel to the needs of an application. So the question is, how do we transparently build efficient and POSIX compliant unikernels? We had two design principles when building Unikraft. One is that we wanted a fully modular kernel. And the second one is that we wanted to provide high performance via specialized APIs. So if we tackle the first one, Why couldn't just we do it with Linux? And to answer this question, we did a graph of all the dependencies between major Linux subcomponents. If you see a line between two such components, it means that there's a dependency. And the number on top of the line means how many dependencies there are. And it should become apparent from this graph that it's not easy to remove one subcomponent without having to do serious engineering work. Instead, Unikraft is built from scratch to be fully modular. And just to give you a little idea, here's two graphs, one for Hello World Unikraft application, and then the bottom one for nginx. I don't want to go into the details, but you can see that they're much simpler graphs. So couldn't you do with existing Unikernel projects? The problem is that, as I mentioned, many of them require significant expert work to build. Many of them are often non-POSIX compliant. So if you want to take SQLite and take it for a spin on a Unikernel project, maybe it's not even supported. And the Unikernels, the part of the operating system is, while still small, is still monolithic. So it's not really easy to take apart. Unikraft is built from scratch to be modular. And of course, we borrowed some pieces here and there so that we're not reinventing the wheel where it's not needed. The second design principle is the specialized APIs. Here's a little example to explain what I mean. Imagine you have an application that wants to do some network processing. It's going to plug into glibc and underneath POSIX sockets, the network stack, and eventually maybe some high performance API. The problem is that while it eventually could go fast, there's all these intermediate layers and it stops it from going fast. Instead, imagine that the application just needs UDP. You could code against the high performance API directly and get high performance. This is a sort of bypass. There's been some work in the past to do this, but in Unikraft, this is really simple to do. And to show you this, here's an architectural diagram of Unikraft. You have the application all the way on top. Underneath, you can plug in into either Muscle or newlib, which is the libcs that we support. And then there's a POSIX compatibility layer. I'll speak more about this later. Under all of that is the core of Unikraft. And the black boxes are these specialized APIs I mentioned. So for instance, just like in the example, if you are concerned about network performance, you could code against our UK NetDev high performance API. If you were interested in retrieving, let's say, static files very quickly, you could bypass the VFS layer and code against directly the UK block dev, having a specialized file system. And I'll show an example of that later. Or for instance, you could plug in different memory allocators. Unikraft allows you to do that. It even allows you to have multiple memory allocators running at the same time. And we'll show some examples of how that matters. So going back to our goals, the first one was that it should be easy to build and run. And there's no better way to show that than a little demo. So here we're going to use Craft, which is a tool that wraps around Unikraft. And we're going to run the up command. We're going to say I want to build nginx at staging. And we're going to call the unikernel my nginx unikernel. And we're going to set that running. What that's going to do is going to fetch all the needed sources. It's going to compile them. And once it's done, it's going to actually run the unikernel, in this case, over KVM. Okay, so now it's up and running. And what we're going to do to make sure it's actually working is we're going to retrieve a static file with curl. We're going to do it once and then twice and a third time. Make sure everything's running, and you can see that it is. Okay, the second goal is obviously easy or no application porting. For this, we target what's called POSIX compatibility, and we have two approaches. The first one is called auto porting. This assumes that we have open sources, like for instance, SQLite, nginx, we have the sources. So we're going to build with a native build system as you normally would. And what we're going to do is take the resulting object files. And by the way, we're building against Muscle. And those object files we're going to link into the Unikraft build process. We have our own ported Muscle in Unikraft. And of course, Muscle expects Linux to be there underneath. It's going to do syscalls. So to cope with this, Unikraft has a module called a syscom shim layer. Under that, we have implementation of syscalls, but of course, those syscalls do not go to Linux, they go to our own Unikraft OS kernel modules underneath. The second approach is called binary compatibility. Here, we don't assume that we have access to the sources. So we begin by taking an application binary, some unmodified ELF. We have an ELF reader and loader module in Unikraft. And then we trap the syscalls and redirect them again to the Syscall machine layer. So obviously, crucially, what matters is how much Syscall support you have, because that directly translates to how many applications you can support. And this is this little block that I showed you in the diagram before that says syscalls. So to give you a bit of background, Unikraft right now supports in the order of 146 syscalls. And for comparison, Linux has over 350 syscalls. And this may seem like it's not much support given how many Linux syscalls have. But as it turns out, you don't need all those syscalls to run applications that you might want to run in the cloud. In fact, a study a few years back came up with this graph, and for instance, it was saying that if you have in the ballpark of 145 syscalls like Unikraft right now, then you could support something like 50% of the applications. Of course, it matters which 146 syscalls. So we did our own analysis. In this case, we took the 30 most popular applications in the Popcon Debian dataset. And here we're plotting the names of them on the x-axis. On the y-axis, we have what percentage of syscalls do we currently have with our 146 syscalls. And if we do support a syscall, we plot it in green. The point here is that most of the graph is green. We already support a number of applications. And for those we don't support, we're just missing a few syscalls. And we are hard at work to support them as well. Just to give you a little taste, we support multiple programming languages and environments. We support applications like SQLite and Redis and nginx, and frameworks such as TensorFlow-Lite. And the final goal was obviously to provide great performance. And the first thing we want to answer is, if we're doing this auto porting and compatibility, are we sacrificing performance in the process? To test this, we're going to compare a manual port of SQLite we did versus this automatically ported version. We take SQLite in this case, and we're going to measure the time it takes to do 60,000 insertions. We're going to plot on the y-axis the time it takes. As a baseline, we took just Linux, and that takes about a second. And we compare that obviously to the manually ported versions on top of newlib and muscle, which also take about a second. The important bar here is this one, which is the auto-ported version on top of muscle. And the good news is that auto-porting doesn't negatively affect performance. Okay, so some more performance numbers in this case, in this area, meaning if I just get an application running on Unikraft, what are the transparent benefits I get without having to modify anything? First, we're going to look at image sizes versus other projects. On the x-axis, we have Unikraft, Hermitax, some other Unikernel projects, but also Linux. We have Lupine, which is a Linux-based Unikernel, and some other projects as well. And on the y-axis, we have image size in megabytes. We did this for nginx, Redis, and SQLite. And you can see that Unikraft needs in the range of a few megs to run all of these applications, and the other projects more. What about boot times? Well, here we measure Unikraft boot times in milliseconds, and then we're going to use a few different virtual machine monitors, QEMU, Solo5, and Firecracker. And we're going to separate the time it takes for the virtual machine monitor to boot and the time that the Unikraft virtual machine takes to boot. First, QEMU takes about 40 milliseconds. It's the slowest one. And you do take a slight hit if you're using actual virtual devices, in this case, a network one. QEMU came in with a more specialized target called MicroVM, and that's faster at 9 milliseconds. But the fastest are Solo5 and Amazon's Firecracker at 3 milliseconds. In terms of minimum memory requirements, again, we're comparing against Linux and other projects. And again, we're using nginx, Redis, and SQLite. And You can see Unikraft takes anywhere from 2 to 7 megabytes. Lupine, the Linux-based unikernel, takes about 20 megabytes, and Linux Alpine about 30 megabytes. What about nginx throughput? Again, we're comparing against Linux and different projects, and on the y-axis, we're plotting throughput in terms of requests per second, actually thousands of requests per second. Just to pick a few points, Linux on KVM is about 100,000 requests per second. Linux native, so not in a virtual machine, is about 175,000 requests per second. Lupine, which is the unikernel based on Linux, is 190,000, and here all the way at the top we have 290,000 requests per second for Unikraft. What about Redis Performance? Again, in this case, we're measuring requests per second against a number of other projects. For gets and sets, I'm not going to read all these numbers, but basically, again, we just about beat Linux natively without any virtual machine. What about boot times with different memory allocators? Here we have 5 different memory allocators that we're trying out that we support in Unikraft, and we're measuring boot time. The default is called binary body allocator, and that is not the best one, so it takes about 3 milliseconds. So instead, we coded a specialized simple memory allocator for the boot time, and that gets us down to half a millisecond, so pretty quick. Obviously, different memory allocators matter in terms of application performance, so we did a test with Redis. Again, 4 different memory allocators, and we're measuring throughput for get and set, and you can see that in this case, memalloc comes out on top, but the point is that the choice of memory allocator matters for the application, and Unikraft lets you easily choose. What about specialized APIs? And just wanted to give you a little taste of what this can do. In this case, we're going to be working in this area of trying to retrieve files as fast as possible. For this, we coded a specialized file system based on the hash table called SHFS. And we're going to compare against Linux in terms of how long, in terms of cycles, it takes to retrieve a file, whether it's there or not. So on Linux using VFS, we're looking at anywhere from 2,600 cycles if the file is there versus 4,000 if it's not there. If we remove mitigations because that hurts performance, you're looking at 2,000 cycles versus 3,200 cycles. And then on the Unikraft side, if we use our VFS layer, you already get significant reductions, about half with respect to the Linux one. But of course, you get the best reductions when you use this specialized SHFS file system, and then you get almost an order of magnitude less, showing that if you're willing to do a little bit of more specialization, you get much higher application performance. And now just a little bit about how Unikraft does on the cloud. In this case, what we did is build a AWS image that can run nginx, and we put it on the marketplace. And here you can see it instantiated on the AWS console. And for the test, what we did is we rented 2 large instances. On one, we put nginx on Debian, so on Linux. And on the other one, we put the same version of nginx on Unikraft, and we measured requests per second. And basically, we got 2 times the throughput. For a second test, we took a large instance and a medium one. On the large one, we put nginx on Linux. And on the medium one, we put the same version of nginx on Unikraft. And we measured again requests per second, and we basically got the same throughput, or said another way, 50% more efficiency. But we wanted to check whether this efficiency would actually translate to dollars savings. To do that, well, you can already look at the pricing table. The difference between a medium and a large instance is about 50%. But even better than that, we looked at our bill for our test, and we spent about $87 for the Linux nginx version, and about $43 with Unikraft, which is about 50% savings. In terms of cloud support, I just showed you we do support running images on Amazon AWS, which is Xen-based. We also support GCP, which is KVM-based. Here's a little console capture of it running there. We also support DigitalOcean, which is also KVM-based. And we have ongoing work to eventually support Hyper-V and Microsoft Azure. Okay, a little bit about the ecosystem. You probably saw the Craft tool in the little demo I showed earlier. Craft is the tool that we now have to wrap everything to do with Unikraft, how to build unikernels and run them. Here's a little output of Craft listing all the modules in Unikraft and the applications that are supported. So you can easily manage lots of different libraries from different sources with it. You can quickly access updates and change versions of applications with it. And you can automatically download application source dependencies. So all you need to specify, as you saw in the demo, is the application you care about, and Craft takes care of the rest. In addition, you can use Craft to retrieve stable and pre-built versions that we regularly publish to releases.unikraft.org. So you don't need to compile things from scratch if you don't want to. And there's lots more commands, and it's constantly growing. I showed you the list command a few slides ago. In the demo, I used the up command to build and run. And we also have a package command that builds OCI compatible instances. This is interesting, and it has to do with integration and deployment that we're working towards. The first part of it is that we're trying to integrate with Kubernetes. The idea would be that you use your standard Kubernetes cluster deployment, and when you say, please start this application or this container, underneath what actually happens is that you're starting a Unikraft virtual machine. So no containers underneath, but as far as Kubernetes is concerned, it's instantiating the container. We're also integrating with Prometheus so that they can actually monitor these Unikraft instances. And we're planning on integrating with Bosch so you can use your Cloud Foundry infrastructure to build actual Unikraft instances. A little bit about the open source project part of Unikraft. Just to give you a little bit of project history, we kicked this off internally at NEC back in 2017. In 2018, we did the public launch along with the Linux Foundation and the Zen project. In 2019, we added a lot of support for different hypervisors and bare metal support along with ARM. 2020, we spent adding a lot of programming language support and application support. And now we're here in 2021, where we are focusing on the sort of higher layers integration with Kubernetes and Prometheus. And I wanted to just give you a little taste for how the project is going. This is a little graph of GitHub stars. And as you can see, we're doing relatively well. We're still a sort of young project. We're doing okay in terms of growth, especially in the past months. Another thing I wanted to mention is just last week, we had a paper published at a top tier systems conference called Eurosys, and we got the best paper award there. So if you have some time, I encourage you to check it out. And you probably saw those 3 colored badges there. What those are reproducibility badges. This means that external reviewers went to this GitHub repo that we put together, tried the experiments in the paper, and got the same results that we did. So I encourage you to go try them out if you want. So basically with Unikraft, we believe that high-performance POSIX unikernels are now a reality. There's lots more information on our website at unikraft.org. As I said, it's an open source project, so you can go check it out on GitHub. And if you want to reproduce the results, there's a separate repo for that. Thank you very much.